pursuit. In 1609, Galileo Galilei pioneered the use of the telescope in order to observe and record sunspots. His detailed sketches, produced over the summer in 1612, revealed that the sun was not a static orb in the sky, but a dynamic force. Galileo's solar discoveries sparked an academic interest in the sun, leading astronomers around to investigate how the sun's life on Earth. 100 years later, astronomers with increasingly complex satellite imagery investigate the origin of the sunspots Galileo first observed.
The sun is different every time you look at it. Those changes in the form we see here, the Earth as well. We call it the vector of the Earth, space weather. The Living in the Stars program was developed at NASA to bring together all the people who study space weather. The Solar Dynamics Observatory is the first mission of NASA's Living in the Stars program. It's designed to study the sun, the root of space weather. SDO has a couple of improvements. The easiest one to think about is we have better cameras. We take a camera that's twice as big as the best one we have in space, and we fly a whole bunch of them on Saturn. Our cameras are 4K by 4K pixels, so that's about 16 million pixels sitting on each camera. We can see images of a full disk of the sun. To see the whole sun in high resolution is better than seeing just a little bit of the sun in high resolution. If we look at a little bit of the sun, and we see something happen, every once in a while we'll see that something came in from the side. So you're sitting there watching it and you say, oh, that's cool, that's what I wanted to study. How did that happen? Why did that happen? So you widen out. So now you see what you wanted to see, and you see that wave come in. But the most important thing is that we're going to take pictures very frequently. The best we've done so far, full disk images of the sun is every 3 minutes, and we're going to take them every 10 seconds. That's a lot faster, and we'll be able to see things that happen on the sun very quickly that right now we skip. We miss. It's like we look at the tops of the mountains and we miss the valleys and we get through them. SDO will also study the amount of energy the sun puts off in extreme ultraviolet wavelengths. These are very short wavelengths that gets absorbed very high up in our atmosphere, causes the atmosphere to heat, expand, and bring satellites out of orbit. Previous missions have looked at the extreme ultraviolet wavelengths every 90 minutes. We're going to look at it every 10 seconds. And we're going to see a lot of new stuff, and we're going to learn about it. The magnetic field is also looked at. We know that this is important because we've never understood the direction of the magnetic field before. That's part of our research, is to figure out what's happening to the magnetic field of something. And by knowing its direction, that gives us another piece of information to understand where it comes from and how it gets converted into solar activity. The instruments on SDO are designed to work together. One measures magnetic field, one measures what the magnetic field does, and one measures what we see that affects us here today. SDO would like to be able to predict space weather so that we can look at the sun, know something's going to happen, and call people up and let them know.
And so you take pictures of the sun, right?
Space Commander log. January 11th. We just double check what we referenced on while we were away. Excuse I don't got my badge or my login information. Well, we'll just do it on my S3 since I got my note doing something else. Well, it appears like my research is right on time.
But when we're flying things in space, astronauts, satellites,
Right on time. What we just overviewed is, like I said, the magnetics are keeping us here. Are safe from the sun. So they're going to diagram alpha.
Very long words for something that's very useful to look at on the sun. Heliophysics refers to the sound that we can measure the surface of the sun that was carefully analyzed.
Heliophysics.
see what's happening under the surface.
Okay, so we can got the, now we can color it.
Much like how we use the waves approach it, and how big it was, and wondering about what's inside the earth. At the same time, H.E.M.M.D.
Just like you can rip a freaking black hole into the universe, man. Jump. That's what I'm creating right there. Here, let's rewind that. That was some good footage. Great footage right there. Astro Geek. Well, I bought this shark so I can study. Alright, now we're going to draw the magnetic field. Papa sitting around here. The asteroid belt. Rough draft, we can redo it. Get the hint. You know. Can't be too close, you know. Well, that's my electric molecule chamber. And that right there creates its own magnetic field. As you can see. No rip. But to get the electrostatic, we gotta have to run the orbits. Then, bam. Partially charged, several locations around the globe. To punch out again. It's the fastest way. I wasted too much time here. So we're gonna continue on research tonight. See up, making good steps. You know, I like to analyze my stuff with NASA, and I'm right on target. Guess that's why I'm Space Commander.